Hi guys, I'd like to welcome everybody to our discussion. So today we're going to handle a topic in chemistry under the molecular shapes. Of course, this is going to appear in some of our discussions, which are going to, of course, come later under the concept of a molecular symmetry. And of course, we may, of course, capture some of the concepts that we have mentioned under the concept of a molecular symmetry in part of our discussion. But basically for today, we're going to look at this concept of molecular shapes, which is going to open for us a window of knowing how we can be able to explain the concept of spectroscopic transitions, and of course some of the areas that we're going to learn under the concept of molecular orbitals. And of course we're going to look at one of the areas under the concept of molecules, which is dipole moments, whereby this particular discussion is going to be relevant in trying to of course tackle some of the challenges that we may encounter under those specific topics. So for today, we're going to look at the different shapes of molecules and try to see how we can be able to explain different, of course, hybridized molecules that we're going to see appearing in some of our discussions. So for that case, thank you and welcome. So as I've said, our topic for discussion today is molecular shapes. And as I've said, this particular conceptual discussion is going to assist us in interpreting some of the areas that we're going to find in our later discussion, which is going to be, of course, as I can mention a few detailing the concept of spectroscopic transitions. And of course, this in understanding the concept of molecular shapes and describing them, we're going to be able to explain the dipole moments of different molecules, or the shapes of these different molecules. And these two particular concepts and others which are going to complement the above are going to assist us in understanding in details the concept of molecular orbitals. So therefore, in order for us to understand this, it will be relevant for us to appreciate the concept of molecular shapes. And today we're going to look at specific types of molecular orbitals. And in this case, we have two specific ones that we're going to look at. So the first one is going to be symmetric, or the one that we are going to describe as symmetry, and number two, and symmetry. So you write this one correctly. And symmetry or unsymmetric aspect of these specific molecules. So for the first one, the molecules which are going to be symmetrical, we can give an example for diatomic H2, which is hydrogen gas, and then we have H for that CH4, which is the methane, and then we have lastly a water molecule which can be illustrated as such. Now for the second category, we're going to look at examples of molecules like the HCl, hydrochloric acid, and then we shall have molecules like chlorine and perhaps HDO, etc. So these are some of the specific examples that I've given, which are going to appear under the broader topics of types of molecules which are symmetrical and unsymmetrical. Now in this case, of course, it will be important for us to look at different forms of molecules, which basically is going to give us their geometrical properties, a description that is going to give us an aspect of geometrical properties. And we're going to look at specifically 5 examples, and then we shall look at specific molecules if time allows us to do so. So for that case, we're going to look at forms of molecules. And the first one in our case is going to be, of course, a linear molecule. Now from these specific terms, a linear, which means the atoms of that specific molecules appear on a straight line, and therefore we're going to see that the angle which is going to be described is 180 degrees. I'm going to give that one using an illustration. Now this one appears mostly in sp hybridized orbitals, sp hybridized molecules, and we're going to see that one of the examples I'm going to give for this is hydrogen, and then we can have HCl given as such. And then next we're going to look at another form of a molecule, which is referred to as trigonoplanar. And from these two specific compound, or rather two names, we can be able to identify the prefixes that are used for this, and the planar, which is a description of a plane. So therefore we will expect this molecule to appear in form of all the molecules, all the atoms of that molecule to appear on the same plane, and in this case as the aspect of a which is a triangle. So therefore we have this range of molecules which are sp2 hybridized, having this particular shape of a trigonoplanar. And an example for this I can give is this particular molecule which is going to assume that shape. And then number 3, we're going to see that we can be able to describe another form of a molecule, which is a tetrahedral structure or form of a molecule, and this one basically appears in the sp3 hybridized molecules, and we're going to see that this is one of the examples that we can give for that. And then next we're going to look at another form of molecule, which is a square planar, and from this is going to have a few similar geometrical aspect of what we have described. So therefore this one appears for the sp3d hybridized, which we can give an example for p2cl4 as one of the examples, specific examples of those square planar. And lastly we shall look at example number 5, or form number 5, which is octahedral, a shape which is specifically, or rather appears for the sp3d2 hybridized. For example, we can give this one, it's going to be a complex compound which I'm going to give at that specific point because of space. So this cobalt, and then I have got this specific part for ammonia, and then we have that is forming a complex ion which is 2 positive. So therefore that's part of the ion. We said this one can be, even the shapes can be allocated for ions and molecules, and therefore for the last case specifically, that's an ion that we're going to see, assuming that a specific geometry. So therefore I'm going to draw specific illustrations for the examples that I've given for the 5 forms of molecules on the board, so that we can be able to discuss them one at a time. I hope the space is going to allow us to, of course, give these different illustrations, but of course I've given 4, and in case we are going to note that in some literature we're going to find this one described as star-shaped tetrahedral, or other names which are of course going to imply the same geometrical shape. So therefore if I start with the first one, which is linear, we're going to see that for this kind of forms, or other forms of molecules, these are going to be of course made up of atoms that lie on a straight line. For example, the diatomic molecules that are given an example for hydrogen gas, which is given as H2. The bond angles is usually 180, whereby it's given as such in case that this one is made up of perhaps 2 atoms. And in this case we're going to see that some of the examples that are given for HCl and of course H2 are going to be shown as such. And we're going to see that for these linear shaped molecules, the shapes are common of course for when the central atom is sp hybridized, as I have explained in the first case. So we're going to see that this one is going to appear for atoms of course which are a central atom which has been sp hybridized. And for instance, we can just give other examples, like in the case of the family of hydrocarbons, can give an example of a triple bond in that particular case. And this is going to be treated as a linear molecule. Now the next one for the planar triangular molecule, this is going to comprise of 3 atoms, just as illustrated for A, B, and C. And then we're going to see that located at the apexes of a triangle. And if I give just the dotted lines here in order to emphasize on that point, this is going to appear like a triangle. So therefore, it's going to comprise of 3 atoms, A, B, and C, which are located at the apex of triangle and bonded to the central atom with a bond angle of 120 degrees. And this is going to describe the planar triangular shaped molecules. And then next we're going to see that the star-shaped tetrahedral structure which I've given. Now in this case I've given solid lines to show the bonding which have been shown. Now for the case of the tetrahedral structure, I've given the dotted lines, of course, which are going to assist us. I try to figure out how that one is going to appear. Now for instance, if you try to complete this specific geometrical shape for this atom, I hope this one is going to be elaborate. Now we're going to see that the angle, the bond angle is going to be 9. It's just an explanation for this, of course, for my drawing. I hope this is going to be illustrated. This is the angle between, suppose this atom A and B. This is the angle that is subtended for that one, which is 109.5 degrees, which is going to give them the maximum distance from each other for the valence shell electron pair repulsion. According to the valence shell electron pair repulsion theory, then we're going to see that this is 109.5 degrees. Now this is common for atoms which are sp3 hybridized, and this is for the star-shaped of course tetrahedral structures, and I've said that these ones are common for the sp3 hybridized, of course central atoms for the tetrahedron molecules. For example, I've given one of the examples for this in my listing, which was CH4 as one of the examples of those. Of course, we can of course include other molecules like ammonia, which are going to exhibit this characteristic of having this particular shape. So the last one we're going to look at this, in this case as by my drawings, the octahedral structure. And for this we're going to see that for the octahedral structure, this is an 8-sided figure, of course with a square base, which I've illustrated using the dotted lines, this particular point, which is the middle point, forming some kind of a plane. And it comprises of 6 vertices on which the atoms are placed, and the central atom in the middle of the 4-sided plane. So in any case, if you try to consider this complete bonds, we're going to have this one illustrated as such. This one bonding to this vertex, another one to this one, another one, and then we shall have this one also appearing as such for the other atoms. So therefore we're going to have this specific shape which has got 6 vertices, and then on which the atoms are placed. And this is common, this particular shape is common for molecules which are sp3d2 hybridized, a central atom which is sp3d2 hybridized, and therefore they are going to exhibit this specific kind of a shape. So therefore we can give an example of SF6, which is going to have, we shall learn about this in details, of course, when we are going to explain these particular shapes as we come across them in our different discussions in the following other videos under this specific concept. Now, as I've already mentioned, some of these particular shapes that we're going to see of the molecules, we're going to describe them using the orbitals that I've mentioned, and we're going to appreciate some of their relevancy when we are talking about the concept of transitions and dipole moments of these particular molecules, especially in the study of molecular orbitals and other areas which are going to encompass molecular shapes. Now, I hope that we have understood a few examples that we have given for molecular shapes, and whenever we come across them, I'll be mentioning these specific videos and giving a link so that we can be able to do a connection and understand this particular topic. So catch us guys in our next videos where we're going to discuss on the similar concepts or other related videos so that we can be able to comprehend this particular wider topic of molecular shapes and molecular symmetry. So that is it for now, guys. Bye. God bless you.